Okay, so now we're going to talk about how to actually compute integrals. Because what we've done so far was just say what it is. But let's see if we can actually do some of them. So, for example, can we do this integral? And our region R, let's just make it simple. Let's just do the square of side length 1 centered at the origin. Okay, how do you actually evaluate this thing? Well, what we did in the 1D situation, we had the fundamental theorem of calculus, which, if you recall, says that the function values of the antiderivative, they actually can be used to compute these integrals. Right? So as long as you can find the antiderivative, then you can evaluate integrals. But a 2D version of this theorem is not actually that satisfactory. I mean, later in the course we'll talk about it, but it's actually not as powerful as the 1D situation. As usual, the curse of dimensionality. This is impossible to get away from. Higher dimensions are always harder than lower dimensions. But what we can do, which is also another unifying principle, is to try to reduce the 2D to 1D integrals. Because we know exactly how to do 1D integrals. Okay? So somehow we want to make this an integral involving just dy, and then there will also be another integral involving just dx. So first we do the dy one, and then the second one we'll do the dx. And that's the best we can do. So, for example, I claim, and this is Fubini's theorem on a rectangle, that the integral over the square xy, you can actually write it first as an x integral on the outside and a y integral on the inside. So, and then you have the same integrand. So first is the y, the one on the inside, and then second is the x one, the one on the outside. So I would put the dy here, and then I would put the dx here. Okay. So that would mean this first integral here to put the limits here too. The first integral is fixing x, or you could say freeze. So that means you integrate with respect to y, and x is just a constant. So you can actually factor that out of the y integral, not of the x integral. So this is y dy. We know how to integrate this. This is x times 1/2 y squared, value difference 0 to 1, so that's just a half, right? So now the second integral is the x integral, 1/2 x dx, and we know how to evaluate this one, so we end up getting a fourth. So that means our original integral is actually equal to a fourth. Okay? So why does this actually work? Why does Fubini's theorem, which is pretty helpful, right? But why does it actually work? Well, if we're just on rectangles, we can just look at the Riemann sums. And remember, an integral is just a sum over the subdivision, right? So it's a sum over the smaller rectangles. Well, that means if you just look at this, we can split it into a y sum and a y sum. So that means the y is on the inside. But then we can also do it the other way too, right? So we can, this is an x sum. This is also an x sum. So actually x is summed first, right? Because this is x1, x2, and that one was y2, this was y1. Right, so that means what we really have here is the integral now over dx first, and then we're doing dy on the outside. Okay, so that's really all there is to it. It's just you're able to rearrange the sums on the Riemann level. So if you want to go to the integral level, just take a limit. And then you get equal signs here, equal signs here. So it's really just Fubini's theorem. It's almost obvious on the level of Riemann sums. It just looks more complicated than it is. Okay, next we'll talk about how to extend this to non-rectangles in the next video.